Hello, my name is Graham Mackenzie. I'm a field applications engineer with Intel focused on the FPGA acceleration of compute. Today I'm going to be talking about the data parallel C++ compiler for oneAPI and how we can use the Intel Dev Cloud to target FPGA. We'll take a look at some tutorials, show you how to use the debugger via emulation, look at some of the reports, and finally compile for FPGA and run on FPGA, all in the Intel Dev Cloud. You can sign up for the Intel Dev Cloud at the oneAPI homepage, which is software.intel.com/oneAPI. Here we scroll down and we find a little link here that says try the Intel Dev Cloud. We'll click on that link and we go straight to the sign up page, and you see as this loads we have this sign up area here. You fill in this information and you click submit. Once you've submitted that, you'll receive an email with login credentials and links for instructions on how to access and how to use the Intel Dev Cloud. We use an SSH config file to configure access to the Dev Cloud. We take a look at this. You'll see it's fairly simple. We have a host name that I provided, my username, an identity file, which is effectively a key that I downloaded based on the credentials email I got supplied when applying for the Intel Dev Cloud, and then finally a proxy command. So if I quit out of this, I can then simply SSH Dev Cloud, and it will load up the Dev Cloud connection. Just takes a few moments, and here we go. I'm logged in. Now that I'm on the Dev Cloud, I need to access one of the compute nodes. I'll do this as follows. Use qsub as the command to submit something to the queue. -L to provide a list of resources. I'm going to say nodes equals 1. I'm going to choose an FPGA compile node. And I'm going to say the processors per node is going to equal 2. And then I'm going to do -d dot to specify the current directory as my working directory, and -i for an interactive session. This just takes a moment to start up. Now that I'm on the compute node, I'm going to create myself a clean directory. Make the demo and change to that directory. And then I'm going to launch the tutorials utility, which is oneAPI-CLI. Now here we are. I'm going to create a project. I'm going to choose a CPP project, and then let's just scroll down and choose vector-add, which is one of the most basic. And accept the defaults and create that in my current demo directory, and then quit. I can now go into that new directory that's been created, vector-add, and start looking at the tutorials. We'll have a look at the README. So this goes through and explains a little bit about the tutorials itself, which is doing a very basic vector-add operation. And then towards the end of this README file, I'll scroll down a little bit here, you'll see that there's some details on how to actually build the tutorial and run it on various targets. So I won't go through that just now. I just wanted to show you how you can look at the README file to understand more about the tutorial and how it works. So I'll quit out of that. Now we can take a look at our source code. So this is actually in a different directory, source vector-add buffers. We start off with a header file and some include files. We'll scroll past that. We're using the namespace sickle, which is used in data parallel C++. Declare some arrays. And then we've got this exception handler. I'm not going to go through this in detail, just suffice to say that this is a standard exception handler that's used in all the tutorials, and we just copy this into our own project. Here we've got the vector-add function. We pass in the parameters for the queue and the 3 arrays, the 2 input arrays and the output array. We declare a range of 1 dimension with a number of items equal to the size of our arrays. Then we create buffers. The buffers are going to store the data on the device, or in our case the FPGA, and then we submit a command group to the queue. via this qsubmit command. We then have some accessors. The accessors describe how the device accesses those buffers. So obviously our inputs A and B are read-only, and our output, the sum vector, is write-only. We then have a parallel for statement, and we include our actual executable code on the device in this statement here. Parallel for means that we're going to submit, in this case, this equation for each instance of I, and I is defined in our range previously. What I'm going to do is I'm going to make this code a little bit more verbose, just to help with the debug process. I'll just scroll down here a little bit, declare some temporary variables like this. So we've got temp A, which is equal to A. We've got temp B, similar thing, equals B. And then we'll have a temp sum, which is equal to temp A plus temp B. And then finally, we're going to do our write back into that device buffer that I mentioned. So this is temp sum, and then just do a new line there. So that's the extent to the edits. We just expanded that one line into 4. We scroll down, we see we've got a function that's going to run on the host. It's going to initialize the arrays, the input arrays, that is. And here we have main. We have a concept of device selectors. So here you can see that if the design is compiled for FPGA emulator, we select the FPGA emulator selector, or the FPGA selector for FPGA, otherwise the default selector. Now the default selector is going to choose a GPU if it's available. If not, it's going to fall back to a CPU. Then we create our initial array objects, we initialize them. We have this try-catch loop here where we define a queue and we print out some basic information about the problem in terms of the vector size and which device we're running on. We call our vector add function, which we showed earlier here, and then we have the catch block. We then compute the sum of the 2 arrays on the host, and we verify it's the same as what's been computed on the device. And then finally, we print out some further information and determine whether we've been successful or not. So I'm going to quit that there. Whoops, escape Q, whoops, WQ. And then I'm going to have a look at the makefile. Now there's a special makefile for the FPGA. All I'm going to do here is just change the optimization, change it to no optimization, which again is going to make debug that little bit easier. And close that there. Now I can go ahead and build this kernel. I'll do that running make FPGA emu for the FPGA emulation target, and then I'm going to specify my makefile being the FPGA makefile. And that should just take a few moments to complete. And there we go, it's done. So if I show you the current directory, we can see we've got an executable here with vector add buffers.fpga emu. And I can simply just run that. Let's do that now. And we can see it's successfully run on the emulation device as shown just in this line up here. So now what we can do is we can actually run this in debug mode. So we'll use GDB and use the specific oneAPI version of GDB and provide our executable, which is vector add buffers.fpga emu. So this launches the debugger, and the first thing I'm going to do is set a breakpoint on our vector add function. I'm going to start the debugger then, and as expected it breaks up main. From this point here I'm going to continue, and we hit our vector add function as expected. So let's change the layout to make it easier to see what's going on. So source layout, and I'm just going to scroll down to see the code of interest, which is that actual vector addition that we expanded earlier. So now I'm going to set a breakpoint on line 87 and continue the code again. So just press C, and indeed we break on line 87. At this point I can print the variables, so temp A, print temp, print temp B, and print temp sum, which should give me the correct answer. So 2,800 plus 2,800 is 5,600. At this point, it can simply continue, and obviously we'll hit the breakpoint again. So let's just delete that, and then we will continue to the end. And it exited normally as expected. Now we'll quit GDB, and I think at this point I'll clear the screen for the next tutorial. So now we're going to have a look at a slightly more complicated tutorial. So let me cd back to the demo directory and launch the tutorial utility again. So this time we'll look at some of the specific FPGA tutorials, which scroll down, you see there's quite a few of them. We're going to choose the loop unroll tutorial. Same thing, create the project and cd to loop unroll, and then we can have a look at the README. As you can see, similar thing as before. We've got a good description here. This goes into quite a bit more detail because it's trying to explain a particular concept, which is loop unrolling in this case. So here we have an unrolled loop. You can see the equivalent code is serial, and then we have a partially unrolled loop, and you can see the equivalent code following there. As I say, this goes into quite a little bit of depth, explaining how it works, and again, the kind of results you should expect, as well as details on how to actually compile the code and run the code on the FPGA. So again, I'm going to quit that and have a look at the actual source code. So let's just take a look at that. Vim source / loop unroll. Similar kind of setup. We've got our copyright header followed by some include files, and again it's a vector add kernel. We've got our device selectors, we've got our buffers. Scroll down and actually see the actual kernel here, and you can see it's a vector add. This time it's actually using floating point as opposed to integer. But if we scroll through the code and try and find the actual main function that actually calls our kernel, we'll see that we actually call the kernel 5 different times, and we're supplying a templated parameter here, which is the amount of unrolling we're going to do. So that's all I wanted to show you from the source code. So I'll quit that. Now, this particular tutorial is built a little bit differently, uses CMake. So to build this code, we need to make a build directory and then cd into that directory. And then from there, we run CMake and reference the high-level directory. Again, this takes a few moments to run through and build the make files. We'll just wait for that. It's doing all its checks to make sure that all the tools are in place, and then it'll get to creating the make file. Because this is a specific FPGA tutorial, there's not a separate make file for FPGA. There's just one make file, and that's only for FPGA in this instance. So that's done, and at this stage I'm just going to build the report. So I'm going to run make report. And again, that's going to go away. What it's going to do is have a look at the code. The compiler is going to run. It's going to determine the data dependencies, produce the RTL code that eventually go through synthesis and create a bunch of reports in HTML format. So that will take, around about 30-40 seconds, generally speaking. Should finish any moment now. And there we go. It's all completed. So when you sign up for the Dev Cloud, you get a credentials emails with your login details and also a unique link. What we do once we're on this page, we hit Get Started. It shows us another page with various different access methods under the Dev Cloud, and we're going to choose this one on the bottom right, which is Launch Jupyter Lab. This will give us browser access to the unique area that we have on the system. I've deleted this file, so I'm just going to dismiss that warning, and then go into our demo directory, the loop unroll, our build directory created, and then as we compiled the code, we got this report, and in the reports directory we find report.html. I'm going to make this a little bit bigger at this stage. I'm going to hit trust HTML and then wait for the report to materialize. So if we're going to look at the summary, I'm just going to scroll down here a little bit, and I want to open this compile estimated kernel resource utilization summary. When I do that, we'll see the resource estimation for the various kernels that we've implemented within our code. Remember, we have different unroll factors. So an unroll of 1 means we're not enrolling, so we have 1 DSP block. If we enroll by a factor of 16, we use 16 DSP blocks. Enroll by a factor of 4, 4 DSP blocks, and so on and so forth, exactly as we'd expect. If I look at the throughput analysis, I can look at our loops analysis. I can click on a loop on the left hand side, and it gives us information such as the actual bit of code, and I've got the code line here. I can click on that. It's pipelined, it's got a iteration interval of 1, which is good, and an estimated Fmax as well as a latency. We look at the system viewers. We can look at the schedule view. So let's pick Vectrad1. As you can see, all the different operations and how they're scheduled, and we can use this information really to understand what's happened in the compiler and make optimization decisions. And finally, if we have a look at the graph viewer, if we click on a node, I'll pick this Vectrad1 again. I have to move my windows around so you can see it, or at least zoom in. And we can see here we've got a cluster of logic. It's a stall-free cluster. We've got another cluster of logic here, and we've got this one here, which is a load, and we've got this one here, which is a store. So this shows us how the compiler has built our code and how it's implemented it on the FPGA. So we'll leave that there and we'll go back to the terminal window. Because a full FPGA compile will probably take about an hour, I'm going to submit that as a batch job. So first I need to create a script. Here we go. I'm going to vim build fpga.sh. Very simple script, just has one command, make FPGA. Save that, then make it executable. Now I'm going to exit my interactive session here, change back to the build directory, and then submit the script. So qsub -l nodes equals 1, FPGA compile, ppn equals 2 -di, all exactly the same, but this time I put in my script. And now I can check the status of this job by running qstat. And you can see there are 2 active jobs here. One is my Jupyter Lab session, and the other one is the new job that I've just submitted. I can keep running qstat to check on the status, but as it says, this is going to take about an hour, and I know that, so I'm going to leave that and come back later. Now that that's finished compiling, we can see what we've got. And as you can see in here, we've got this loop unroll.fpga executable. So this is ready to run, but first I need to create a new session, and this time I'm going to target an FPGA runtime node. Now the FPGA runtime node actually physically has the FPGA card in it, as opposed to the compile nodes, which just have the resources available to build the executable. So qsub again, -l nodes equals 1 FPGA runtime, ppn equals 2-d.-i for interactive again. That's waiting for a free resource, which is found. Just waiting for it to make the connection, and there we go. And I can now just simply run that executable. So this prints out the array size, then the unroll factors and the execution time. And as you can see what's happening here, we're seeing approximately a doubling of performance at each doubling of unroll factor, which again is as expected. Maybe what's not expected is we start flattening off towards the end. And the reason for this is because we go from being compute bound to being memory bandwidth bound. And so adding more and more compute when your bottleneck is actually the memory bandwidth is not going to help anything. And that's illustrated here in this tutorial example. So we've seen how we can use the Intel Dev Cloud to learn more about data parallel C++. We've had a look at some of the tutorials and seen how we can debug and run those tutorials on the emulator. We also had a look at the reports. These will help us optimize the code to get the most out of the FPGA. And finally, we ran the resultant executable on the FPGA, all within the Intel Dev Cloud. To learn more about the Intel Dev Cloud, take a look at the links that are in the email you will have received when signing up for Dev Cloud Access. To learn more about data parallel C++, I recommend this book here. You can obtain and download an electronic copy of this book via the link that's in the video description, or you can order a printed copy like I have here. Thanks for watching.